This is example 6, unidirectional conduction in a cylinder. We have here a stubby cylinder that's 5 centimeters tall with a thickness of 1 centimeter in the radial direction. And the internal temperature is isothermal at 40 degrees C, and the external temperature is isothermal at 20 degrees C. And the question asks us, how much heat must be supplied? And so the heat question triggers us to use Fourier's law. The second part of the question is, what is the temperature profile? And so the words temperature profile trigger us to use the heat equation. So this example will demonstrate both the use of Fourier's law and the heat equation applied to a cylindrical geometry. The material is copper, so we look up the thermal conductivity for future use, and we'll start right in with Fourier's law. And the first part of the question is literally asking for this heat flow rate that we need to maintain these isothermal conditions. So we need to, in order to solve for Q, we need to integrate Fourier's law. It's an ordinary differential equation, first order, linear, non-homogeneous, but it's still separable. So we go ahead and we'll separate and integrate that equation. So I'm going to choose as boundary conditions that the inner radius R inner, Ri, has temperature T inner, Ti, and the outer radius Ro has temperature To. We'll later replace those with the boundary conditions specified in the problem, but I'm leaving it in the generic form so that this is basically the general integrated form of Fourier's equation for a cylinder. And if we go ahead and perform that integration and apply those generic boundary conditions, we can solve for the heat flow as a function of the temperatures, the radii, and physical constants like the length of the cylinder and the thermal conductivity. So all we have to do to solve this heat flow is plug in the parameters that we already know. And I've converted the lengths into units of meters. And it's a little bit tricky for the radii because I gave you that the circumference, the outer circumference is 15 centimeters. So we need to back calculate what the outer radius is. And then the inner radius is just 1 centimeter less than the outer radius. So those are where those expressions come from. If we perform the calculation, we get that the heat flow rate required to maintain these temperatures is 4,630 watts. Problem solved. Now, if we think about this a little bit, cut open that cylindrical shell and basically uncurl it. And what you have is something that looks a lot like a slab. And the slab is 5 centimeters high, 1 centimeter thick, and 15 centimeters long. Keep the exact same boundary conditions, and this should look familiar. This is exactly the problem that you solved in example 1, a copper slab with heat transferring through, given exactly this geometry and boundary conditions. The interesting thing is that when we solved it in the slab geometry, it took 6,000 watts to maintain the temperature, and for the cylindrical geometry, it only takes 4,630 watts. And actually, I won't tell you exactly why that is because I think you can figure it out. Think about the way the area is changing for a cylinder as opposed to the slab geometry. But that's just a useful observation. Now, the next part of our question is asking for the temperature profile, and so we need to use the heat equation to find that. And we're going to assume that there's no generation, that it's at steady state, and that the thermal conductivity of the copper is constant. These are all pretty good assumptions. And we'll just write out the heat equation that we derived. This is the form. And what we need to do is solve this and then apply the boundary conditions in order to calculate our temperature profile. So it's second order, it's linear, it's homogeneous, and it also happens to be separable. So we separate out the equation, and we have a second order derivative on the left-hand side and a first order derivative on the right-hand side. But that left-hand side is a little more complicated because it multiplies two terms, so we're actually going to have to use integration by parts. And this is a different solution technique than shown in your course notes, but you'll see that we recover the same answer as you would expect. If we apply integration by parts, I'm just going to skim through the math relatively quickly. I always have to write the expression out for how you solve the integration by parts. So in this case, we're going to call u equal to r, and we're going to say dv is d squared t dr squared dr. And then you can plug those values into our little formula derived from the chain rule and basically recover that the left-hand side is r dt dr minus t, and then integrating the right-hand side is pretty simple. It's just t plus a constant of integration. Temperature cancels, and we have one more integration to perform before we can get back our temperature profile. The second time we separate and integrate, it's a lot more simple, and we get this basic temperature profile for the temperature across the cylindrical shell. To solve for the constants of integration, we apply the boundary conditions. And so our first boundary condition is that the internal temperature is 313 Kelvin, and from our calculations for part 1, we know that the internal radius is roughly 0.014 meters. The second boundary condition is the external temperature is 293 at the outer radius, which is about 0.024 meters. And you do need to actually use a few more significant figures to get an accurate answer. But two equations, two unknowns, you can solve for it and then plug those back in to get our temperature profile through the thickness of the cylindrical shell. So that is the answer we're looking for. And just to be sure that we calculated that correctly, let's go back and double check that our Q value is correct. So we know that from Fourier's law, Q is related to the first derivative of temperature. And we've just calculated a temperature profile. So let's differentiate it and double check that we get back the heat flux we calculated in the first part. So if you differentiate the temperature profile, you get a constant and an inverse R dependence. And we'll just choose any R value. It should work for every potential value within the thickness of this copper shell that we choose. What you see is that the R value actually cancels out, so that the heat flow rate, is only dependent upon these constants. And if you work that calculation out, indeed, you get 4,630 watts as before. So this just verifies that we've likely calculated everything correctly. So our last step is to evaluate the difference between the slab and the cylinder profile. Slab, it's a linear temperature profile. Cylinder, it just dips down slightly faster in temperature across the thickness of this differential shell. And so, the end temperatures are the same in both cases, but the cylinder takes less heat to maintain that temperature difference, and it has a slightly nonlinear temperature profile. And so I have one last question, which is this why doner kebab is cylindrical?